So we shall first recall the lemma that we have done in the previous lecture. So lemma, the lemma states that if T is a linear operator, let T be a linear operator on a vector space V, and let lambda 1 to lambda k be the distinct eigenvalues. Be the distinct eigenvalues of T. Now for I running from 1 to k, let Vi belong to the eigenspace corresponding to lambda I. If this V1 plus V2 plus Vk is equal to 0, then we have shown that Vi is equal to 0 for all I. This was the lemma that we have done in the previous lecture. Now we will take up a theorem. Let T be a linear operator on a vector space V and let lambda 1 through lambda k be distinct eigenvalues of T. Be distinct eigenvalues of T. For each I from 1 to up to k, let Si be a linearly independent subset, of eigenspace corresponding to lambda I. Then the set S, which is equal to S1 union S2 union so on union Sk, is a linearly independent subset of the vector space V. So if T is a linear operator on a vector space, in fact, let Si be a finite linearly independent subset. So finite term is necessary here. If T is a linear operator and these are the k distinct eigenvalues of T, and we are defining Si to be a finite linearly independent subset of the eigenspace corresponding to lambda I, then the union of these Li subsets corresponding to lambda i's is a linearly independent subset of the vector space V. Now the proof: suppose for each I from 1 to k, Si is equal to the set consisting of the vectors Vi1, Vi2, so on, Vi ni. Since we are assuming Si is to be finite, so let the cardinality of Si be equal to ni. So that is we are writing S1 as V11, V12, V1n1. S2 as the set consisting of the vectors V21, V22, V2, n2. and so on, and Sk as Vk1, Vk2, Vk, and K. So then S can be written as, now S is the union of these SIs. So S is S1 union S2 union Sk. Now it can be written in compact form as Vij, where 1 is less or equal to I is less or equal to K, and 1 is less or equal to J, and less or equal to Ni. Now we have shown that this S, which is the union of these linearly independent subsets from the eigenspaces corresponding to lambda i's, is a linearly independent subset of the vector space V. Now consider any scalars. Consider any scalars Aij such that this summation I from 1 to k, summation j from 1 to ni, aij, vij is equal to 0. So that means this is a linear combination over all the vectors in the set S. So then that is, now substitute different values of I here. We try to expand this to have a better look at this summation. So the first term when I is equal to 1 is summation j from 1 to n1. This is a1j v1j. Then plus second term is summation j from 1 to n2 a2j v2j. Then plus so on. And the kth term is summation j from 1 to nk akj vkj is equal to 0. Now this sum can be written as, so let wi be the ith term in this sum. So let wi is equal to summation j from 1 to ni a ij v ij. So let this wi be the ith term in the sum. So this is the first term, this is w1, then this is the second term, which is here w2, and this is the kth term wk. So let wi is equal to this thing. So then we have then w1 plus w2 plus so on plus wk is equal to 0. Now here we can use the previous lemma. Now this lemma states that if vi's are the eigenvectors from the different eigenspaces, then their sum is equal to 0, means that every vi is equal to 0. Now if we have a look at this w1, suppose, then w1 is equal to this summation. Now here, let's see what is this w1. Then this is equal to summation j from 1 to n1 a1j v1j. Now if we expand it, this is a11 v11 plus a12 v12 plus so on plus a1n v1n. Sorry, a1n1 v1n1. So this is w1. So now let's have a look. What are these vectors? v11, v12, v1n1. Now this is v11, v12, v1n1. So they are the vectors from S1. So this means that this w1 belongs to the eigenspace corresponding to lambda 1. Because this v11, v12, vn1, this is a linearly independent subset from the eigenspace of W1. So this W1 belongs to the eigenspace corresponding to lambda 1. Similarly, so actually this, so that is, similarly we can show W2 is a linear combination of the vectors from S2 and so on. So that is this Wi belongs to the eigenspace of lambda I. Now we have these Wi's from the eigenspace of lambda i's, and lambda i's are the distinct eigenvalues. So using this lemma, where we had chosen the eigenvectors from the different eigenspaces corresponding to distinct eigenvalues, then their sum equal to 0 means that actually this is a linear combination where each of the coefficients is equal to 1. Then this linear combination equal to 0 means that every vi is equal to 0. So therefore, from here we get every wi is equal to 0. Thus, each wi is equal to 0, where I is equal to 1, 2, up to k. So therefore, this first term is separately 0, second term is separately 0, and this last term is equal to 0. So that is, when wi is equal to 0, it means summation j running from 1 to ni aij, then vij. aij into vij, this is equal to 0 for all I running from 1 to up to n, up to k. But now let's have a look what is the summation j running from 1 to ni. So now summation j running from 1 to ni aij vij is equal to, now this first term is equal to ai1 vi1, then second term is ai2 vi2, then so on, and the last term is a I n1 vi n1. Now let's have a look where are these vectors vi1, vi2, and vin1. So here we have these vectors vi1, vi2, vini. Sorry, it is ni here. So this is vin ni, because this is summation running from j to 1 to ni. So this is I from 1 to ni. Now this vi1, vi2, vini, they are the vectors from Si, but Si is a linearly independent set because we have chosen that Si is linearly independent subset of E lambda I. So therefore here this vi1, vi2, vini, this linear combination is actually the linear combination of the linearly independent vectors in Si. So this is equal to 0, but this vi1, vi2, vini, this set is actually the set Si is linearly independent. This set is linearly independent. So thus, from this equation, ai1 is 0, ai2 is 0, and aini is 0. And similarly, from the left-hand side, when we give different values to I, and then different values to this j, we get aij is equal to 0 for every ij. So thus, aij is equal to 0 for all 1 less or equal to j less or equal to ni, and in fact for 1 less or equal to I less or equal to k. So therefore S is linearly independent. So we have shown that S is linearly independent. Now let's take a theorem on the diagonalizability of a linear operator. Let's state the theorem here. Let T be a linear operator. Let T be a linear operator on a finite
It's 5 o'clock.
Dimensional vector space on a finite dimensional vector space V such that the characteristic polynomial of T splits. Now let lambda 1 through lambda k be the distinct eigenvalues of T be the distinct eigenvalues of T. Then this linear operator T is diagonalizable. Then the linear operator T is diagonalizable if and only if and only if the algebraic multiplicity of lambda I is equal to the dimension of is equal to dimension of the eigenspace corresponding to lambda I for all I. Now algebraic multiplicity, if the algebraic multiplicity of every lambda I equals the dimension of the eigenspace, and dimension of eigenspace is also known as the geometric multiplicity of an eigenvalue. So this theorem states that if arithmetic algebraic multiplicity of an eigenvalue equals the geometric multiplicity of the same eigenvalue, then the linear operator T is a diagonalizable linear operator. So therefore, for every eigenvalue, if for all the distinct eigenvalues, if the algebraic multiplicities and the geometric multiplicities are identical, then such a linear operator has to be a diagonalizable linear operator. So in order to prove this theorem, we have to prove two parts. First, we will assume that the linear operator is diagonalizable and show that the algebraic multiplicity of a lambda I equals the dimension of eigenspace corresponding to lambda I. And then conversely, we will assume that algebraic multiplicity of lambda I equals the dimension of eigenspace of lambda and show that the linear operator is diagonalizable. So let's start the proof. First, let's fix some numbers that denote these algebraic multiplicities and dimension of the eigenspaces. For each I, let mi denote the algebraic multiplicity. The algebraic multiplicity of the eigenvalue lambda I, and let di be the dimension of the eigenspace corresponding to lambda I. Okay, now first suppose that T is diagonalizable. Suppose that T is diagonalizable. we have to show that this mi is equal to di. To show mi is equal to di for all I. Now for this, as we have seen, supposed that T is diagonalizable, therefore by definition, we have a basis consisting of the eigenvectors of T. So now let beta be the basis consisting of eigenvectors of the linear operator T. And for each I, define beta I is equal to beta intersection the eigenspace corresponding to lambda I. So now beta is the basis of T, beta is the base of phi consisting of the eigenvectors of T. And this comes from the fact that we have supposed T is diagonalizable. Now this beta I, it's the set of those vectors from beta, which are the eigenvectors corresponding to lambda I. So therefore this beta I is the set of vectors that is defined beta equal to this as the set of vectors in beta that are eigenvectors corresponding to lambda I, that are eigenvectors corresponding to lambda I, and let the cardinality of beta I be equal to ni. Then we have these equations. Then we have. Now since if we take so therefore the cardinality of beta 1 is n1, cardinality of beta 2 is n2, and so on, and cardinality of beta k is nk. So we have n1, in fact we have like this. Then we have cardinality of beta 1 plus cardinality of beta 2 plus cardinality of beta k. Now this is equal to n1 plus n2 plus so on plus nk. And in fact, this will be equal to n, where we are assuming n is the dimension of the vector space V, which is actually the cardinality of the basis beta. Now beta is a basis and V is finite dimensional. Let its dimension be n. Beta I has order ni, so the sum of all these orders must be equal to n. Also we have this m1 plus m2 plus mk, which is the sum of all algebraic multiplicity of all the eigenvalues. This is also equal to n. Because if we have a linear operator on an n-dimensional vector space, then the number of eigenvalues is equal to n. So that means the sum of all algebraic multiplicities is equal to n. Now we have. So now as cardinality of beta I is equal to ni, and dimension of the vector's eigenspace corresponding to lambda I is equal to di. So we have this ni is less or equal to di. Now this beta I is the linearly independent subset from the basis beta, which consists of the eigenvectors corresponding to lambda I. So therefore, each of the vectors in beta I is from the eigenspace of lambda I, and since beta I is linearly independent and a maximum possible number of linearly independent vectors from lambda I is equal to ni, because is actually equal to di. Now we are choosing a linearly independent subset beta I from the eigenspace of lambda I. So therefore, the number of eigenvectors in number of elements in beta I will be at most equal to the dimension of the eigenspace corresponding to lambda I. But now this dimension of lambda I is equal to di, so this beta I has cardinality less or equal to the dimension of the eigenspace corresponding to lambda I. So that is why we have ni is less or equal to di for all I. For all I. Now again, we have by some previous theorem also, we know that geometric multiplicity of an eigenvalue lambda is always less or equal to the arithmetic multiplicity of an eigenvalue lambda. So thus, now geometric multiplicity is the dimension of the eigenspace. So thus we have this di is less or equal to the arithmetic multiplicity, that is mi for all I. So combining these two things, therefore we obtain this ni is less or equal to di is less or equal to mi. Now this gives now taking the summation from I from 1 to k. So this gives a summation I running from 1 to k ni. This is less or equal to summation I running from 1 to k di, and this is itself less or equal to summation I running from 1 to k mi. Now we have already seen that the sum of ni's is equal to n, and the sum of mi's is also equal to n. So this gives all of these inequalities are actually the equalities. So this gives a summation I from 1 to k, this mi minus di is equal to 0. But we have this mi is greater or equal to di, but mi minus di is greater or equal to 0, and it is from this equation. So we have, so each term in this sum, so each term in summation mi minus di I running from 1 to k must be equal to 0. Must be equal to 0 because we have the sum of these k terms is equal to 0, but mi is greater or equal to di. So every term in the sum is a non-negative term, but the sum being equal to 0 means that every term must be equal to 0. So thus, mi minus di is equal to 0 for all I. So therefore, mi is equal to di for all I. So that is this mi. This is the dimension of the eigenspace corresponding to lambda I. So therefore, we have proved one side of the theorem. Now, conversely, assume that mi is equal to di for all I from 1 to up to k. we have to show that T is a diagonalizable linear operator. For each I, for this, we do it like this. For each I, let beta I be an ordered basis for be an ordered basis for the eigenspace corresponding to lambda I, and let beta is equal to beta 1 union beta 2 union so on union beta k. Then beta is linearly independent. And this is by the previous theorem. So let's have a look at as what was our previous theorem. The previous theorem was that if S1, S2, Sk are the linearly independent subsets of the eigenspaces corresponding to lambda i's, then their union is a linearly independent set. Now, here in this theorem, we have beta 1 is a basis of E lambda 1. So beta 1 is a linearly independent set. Beta 2 is a linearly independent subset from the eigenspace corresponding to lambda 2. Beta k is a linearly independent set from the eigenspace corresponding to lambda k. So therefore, their union is a linearly independent subset of V. This is a linearly independent subset of the vector space V. Furthermore, since this Mi is equal to Di, since Di is equal to Mi, for all I, we have summation I running from 1 to k Di is equal to summation I running from 1 to k Mi. But now the sum of all algebraic multiplicities, this is equal to the dimension of the vector space n. So thus, the cardinality of beta is equal to n, because this di is the cardinality of beta I. So therefore, and these beta i's are obviously pairwise disjoint, because beta 1 is a basis of E lambda 1, beta 2 is a base of E lambda 2, and a single eigenvector cannot correspond to two distinct eigenvalues. So therefore, these beta i's are pairwise disjoint, and order of the beta I is equal to di. So the cardinality of beta is equal to n, which is the sum of all these di's. But these di's sum to the sum of mi's, but these mi's sum to n. So summation of all di's is equal to n. So cardinality of beta is also equal to n. So therefore, we have constructed the basis. So thus, beta is a basis. This is a basis of phi, because dimension of phi is assumed to be equal to n. But now beta is consisting of the eigenvectors, because these beta i's, all of them contain the eigenvectors corresponding to lambda i's. So therefore, this beta is a basis which consists of the eigenvectors of T. But beta consists of the eigenvectors of the linear operator T. And so by definition, so thus by definition, T is diagonalizable. So this completes the proof.